Our goal is to define Sobolev functions on metric measure spaces. A metric space together with a measure that is at least Borel to have some connection to the metric structure. We have been talking about Poincare inequalities using only Lipschitz functions and their pointwise Lipschitz constant as their derivative. But this is kind of also jumping ahead of ourselves because we are yet to define even our first class of Sobolev functions. In this video, I talk about the history of different types of Sobolev spaces that have been defined. This is an area of mathematics that we're fortunate enough to know the full history behind, at least up to much finer details. We kind of know what papers were the first, and that is the type of thing that we usually don't have available for older theories. So historically, the first Sobolev class in this abstract setting is due to Korevar and Schoen. So given usually imagine p is between 1 and infinity, just to avoid these technicalities with p equal 1 and p equal infinity cases. So again, this video is just an overview of the definitions and not precise, rigorous stuff, except when I claim them to be so. Okay, so technically the space they define is not giving us when a function from a metric space into R is, say, in the right Sobolev class, but it has been modified, and one can easily do so and use the energy they have to come up with a notion of Sobolev functions of this sort. So with the metric source and say Banach target or real valued target. So I'm not going to talk about this space in more detail. Then in 1994, Piotr introduced what is now known as a hajlasz Sobolev space. And the paper which contained this is actually published in 96, so it's a bit confusing. For example, there is a paper in 95 talking about this space and proving more stuff about it, but the original paper where this object was born is published in 96. So usually even gaps of 3 years when I was looking at literature has occurred. So I will do a separate video of the actual papers and their titles and number of pages and things like that, which you can refer to also read up on the literature for yourselves. But anyway, so Hajlasz's amazing observation was a way to identify Sobolev functions in Euclidean space without ever using any Euclidean structure. So remember that W1P, the Sobolev functions in the Euclidean setting, I'm not even talking about a subset, an open subset of it, it's just the honest Rn with the Lebesgue measure. How do you define these functions? So you talk about partial derivatives. So f is your measurable function, and you take a smooth function and you take its partial I. If you can find a function gi, because it depends on I, so that this equality holds for every, say, compactly supported smooth function on Rn, then you say that gi is your partial of this fi, the weak partial derivative in direction I, and then if these belong to LP, as does f itself, then you call this function a Sobolev function. But look how much Euclidean stuff goes into this. You need to be able to talk about smooth, compactly supported functions. You also need really the foliation structure, because you're talking about partial derivatives in direction I and then in direction j. Okay, it feels a bit superficial, but how are you going to get rid of this structure when you talk about just a metric space and a measure? The metric space need not even be connected necessarily. So this is what by definition a Sobolev function in Euclidean space is. What Piotr Hajlasz observed was that a function that is in LP is a Sobolev function if and only if there is another non-negative function g, which will act like the derivative, and that's why this is also often referred to as Hajlasz gradient, such that the values of the function are controlled by this function g. That is why it's called the derivative quotation or the gradient of the function. So this is, for example, if g is, say, a bounded function, you put that bound here, this means that f is Lipschitz. And Lipschitz functions are, quite important in the theory of Sobolev functions. So if you know a bit more about Sobolev spaces, Sobolev functions in Euclidean case, you know that they can be approximated by Lipschitz functions. So definitely this points in that direction. But anyway, so the direction when you start with a function here and you want to prove that there is such a g is more straightforward. So the function that will do the job is the maximal function. So g at a point will be the maximal function of the gradient of u, if you are familiar with this. So in this case I'm using f, and then evaluated at x, or maybe the maximal function is actually truncated up to something. Yeah, so the significant thing is the backward one, that if you start with a function, if you start with an LP function which happens to satisfy this inequality with some other choice of g, then actually it is a Sobolev function, and all the fine properties of Sobolev spaces, all the higher integrability, Sobolev embedding, and everything follows for this f. And when you look at this inequality, you see that there is no Euclidean structure used there. There is definitely no mention of coordinate directions. There is no mention of smooth functions, and that's it. So, and that was the amazing observation which led to Hajlasz defining the space M1P. So basically I have given you the definition of M1P for a general metric measure space. All you need is a measure to be able to talk about LP, and you need a distance because this absolute value of x minus y is just distance of xy, and functions are real valued, so this side does make sense. So this star inequality does make sense in an abstract metric measure space. So you can define those functions f for which this inequality holds, the Sobolev functions on your space. And then you can define a norm by minimizing over the smallest in the LP norm of such g. Okay, so we're not gonna, in this video at least, get into details of this. And then fast forward around, again, these are not like strictly chronologically ordered stuff because things were happening simultaneously and whatnot. But around 1998, at least that's when this important paper of Heineken and Koskela came out about the theory of quasi-conformal maps between metric spaces. And in the quasi-conformal theory in the Euclidean case, so quasi-conformality, at least in one definition of it, is purely metric definition, uses no other structure. But then the famous classical theorems were that if you have a quasi-conformal map between domains of Rn, then the function actually turns out to be much nicer than the definition predicts. It does belong to the Sobolev space, W1n, and it's absolutely continuous on almost every curve, and many other properties of quasi-conformal maps actually followed once this observation, this analytic characterization was found. So obviously people were trying to do similar things for quasi-conformal maps between metric spaces. So if you have a quasi-conformal map defined again metrically, what more can you say about it? Is it absolutely continuous on almost every curve and things like that? So studying such questions led Heineken and Koskela to come up with the notion of upper gradients. In that paper from 1998 in ACTA, so I remember it as ACTA paper because Pekka Koskela always mentions, if he refers to it, he says it's in the ACTA paper. So the upper gradients were found, which in that paper were called very weak gradients. So the notion of upper gradient is saying that there is a function. So a function g is an upper gradient for a function f if whenever you have a path between x and y, whatever path you take between x and y, the difference in the values at the end points is governed by integrating this g along this path. So you need definitely a way to integrate this. That's g being Borel is enough. And the other thing is that these paths need to be rectifiable. So this is a good notion when you have a lot of rectifiable path between points in a space, when the space is quite well connected. So, and then ideas behind this. So in that paper, upper gradients, their importance, they were defined. They were literally born there. And then the importance of Poincare inequality was also really illustrated there. And the ideas there led Nageswari Shanmugalingam in 2000 to define what is called the Newtonian Sobolev space. And the notation often is N1P of the space X, and for the Newtonian, because the Sobolev spaces built in N1P are defined via this inequality. And this inequality really is just a generalization of the fundamental theorem of calculus. So remember, in fundamental theorem of calculus is just saying that this is equal to integral of f prime dt between points x and y. And if you put absolute value inside, then it says, okay, x to y, and then f prime dt. So this is really a fundamental theorem of calculus, but not for path on the line, but in abstract metric setting. But the core idea is really the fundamental theorem of calculus, and that's the elegance of it. In both theories, after the theorems are proven, the end result is so simple and elegant. You can just, like here, I just explained the theory of Sobolev spaces in one line to you. Even defining this one in Euclidean setting is a pain. Okay, so that's how this Newtonian Sobolev space was born. I probably should have inserted first Jeeger's work, but actually, so the preprint for this is from 1998, because Jeeger's work, which is from 1999, actually references a result from this preprint. So Jeeger defines a different space. Let's call it CH1P. I'm following a reference that I will talk about in a minute. So, but then under very mild conditions, actually, I think it's enough just to have the measure doubling. This becomes, so the Shanmugalingam result proves that this is actually just N1P. So it's defined differently, but it ends up to be equal with this. Another work, I think this is from 1995 or maybe a later work of Piotr and Pekka Koskela, they define a Sobolev space where they take the Poincare inequality as the very defining property of Sobolev function. So they define the Poincare Sobolev space P1P over X by literally saying those functions in LP of X belong to this space if they satisfy P Poincare inequality with some other G in LP of X. So that means here this G becomes the, again, quotation mark derivative. If there is another function in LP, so that the Poincare inequality that we've talked about so often, if the Poincare inequality holds, then we say this F actually belongs to the Sobolev space. So this is yet another one. So as you can see, there isn't one definition of Sobolev spaces. Okay, that reference that I was talking about is this amazing book that is probably the first book really on the topic, the first book that brings everything that was scattered in literature into a book form. So Sobolev spaces, on the title is Metric Measure Spaces, and then the secondary title is that an approach based on upper gradients, which I kind of defined up there. So this control, so just this G is called an upper gradient of the function f. So its integral along curves controls the oscillation of the function at the endpoints. So this book is by Heineken, Koskela, Shanmugalingam, and Jeremy Tyson from 2015, but the work on that had already started much earlier. Actually, Heineken had passed away by the time it was published. So you can see it's by the big names in the theory. So this therefore focuses on the space N1P of X, but it has a chapter devoted to other notions of Sobolev spaces. In particular, in their theorem 10.51, if my numbering is correct, has this one, that if mu is doubling, which is usually the least that you assume on a space, and for values of p bigger than 1, so M1P, this high-wash Sobolev space, is inside the Poincare Sobolev space on the same, of course, space X, and this is inside the Korever-Schoen space, and then all of them are inside the N1P space, which we already mentioned is the same as the Jeeger space. So this is just under the doubling of the measure assumption. This is the relation between them. And now, for the first time, I am happy that I had started talking about Poincare inequalities much earlier than even defining any single one of these. Because the next result is that if you have, so this is 10, 5, and 3. Also, these are Banach spaces, and these inclusions are not just as sets, but rather kind of embeddings. So the norms are comparable. So this says that if mu is doubling, and now the thing that I have emphasized so many times, that the existence of Poincare is so important. So p again bigger than 1, and X supports a Q Poincare inequality for some Q strictly better than P. We remember that Poincare inequalities, it's better Poincare inequality if you can push the exponent down. So we don't want P Poincare, we want strictly better Poincare. So for some Q strictly better than P, then, so if we have these, then M1P is nothing other than P1P, and that is nothing other than KS1P, and that's N1P, which was already Jeeger 1P, and that's amazing. So this brings everything together, that in the spaces that have doubling measure and support a Poincare, we have equality, and all the norms for these Banach spaces are comparable. In particular, if you are in Rn, or a nice subset of Rn, so that the Lebesgue measure is doubling, and we know that the space supports actually one Poincare, so already you have this Q here. Then we see that for P bigger than 1, all of these are the same spaces, and actually they are equal to this W1P, the classical Sobolev space. So in case of Rn, we have all of them equal to the classical Sobolev theory. A point on here, and this was, so there is a very, very important, a pivotal paper in the theory by Keith and Jean in Annals from 2008. So they say that if your space is complete as the metric space, then if you have P Poincare, so if you are under this doubling, so let's say doubling and complete metric space, then if you have P Poincare inequality, then basically for free, so this is called the self-improving property, you have Q Poincare for some Q strictly less than P, which was just a big paper. It proved so many conjectures and improved so many results, because up to that point many results in this theory looked like this one. So you work with a P and you have assumptions, but then you're not happy with P Poincare, you wanted something a bit strongly better, and it wasn't known that if you can always just go down free. So if you combine this result with that, then you will just avoid this intermediate annoying Q parameter here. So the result improves just to saying that if you have a complete space with a doubling measure, and if you have P Poincare, then these are all equal, no mention of that. But yeah, all due to this amazing paper. So it's not really a strict thing, because, well, if you're working with parameter P, it's annoying to say that, to claim that there is a strictly smaller parameter. Okay, so the last comment regarding this. So because this space here is the biggest, so why would we not just ignore all the previous smaller ones and work with that? Because this is the largest class of Sobolev functions that we get, right? The point is that, okay, you can define anything you want as Sobolev functions, right? But what properties do you get for them? Remember, something deserves to be a Sobolev function, for example, in the Euclidean setting, if it has much better properties than just a random measurable function. For example, you may have seen that Sobolev functions have traces. So if you have this omega, which is a Lipschitz domain, if you have a Sobolev function here, then it has a trace value, a boundary value. You cannot assign any boundary value to the measurable function, but Sobolev functions do. Another thing is that if you are in W1P, then F is actually in some LQ, so Sobolev embeddings. actually if P is bigger than N, you get that F has some representative that is actually Holder continuous. So many more things. These are actually called under the name fine properties of Sobolev functions. So they need to have more delicate properties than just a measurable function. So depending on the metric measure space that you have, this can actually be too large. So if your space, for example, has no rectifiable path, for example, it's this snowflake, then this becomes all of LP functions, because it turns out that the zero function is an upper gradient because there are no rectifiable curves. So you don't really need to test it against anything. This will be just x equal y. It's true. So then LP, everything in LP will be there. And so you cannot expect any finer properties. So your Sobolev function is no better function than a measurable function, basically. So in that case, this space will be a better one. For example, for these functions, by this inclusion, Poincare inequality holds. For these, it won't hold because, again, you take a non-zero LP function and its gradient, its derivative, upper gradient in this case, will be just 0, 1. So there is no Poincare here. That's also why having Poincare allows this, and not having is bad news for this equality. So there, depending on the how many rectifiable paths you have on a space, you could have the larger spaces too large so that the functions there do not have the nice properties we expect from a Sobolev function, and the smaller spaces may have better properties. Another reason why you want to work with all of these is proving something, proving the same claim for functions here might be much easier, say, proving the same property for function there, because of the way they are defined. For example, this is already defined, you saw, through a pointwise inequality here. For example, if you want to approximate a function by a Lipschitz function on a large measurable set, this is very easy to work with because you take just a large measurable set on which this G is bounded, and there you go, F becomes Lipschitz. So, so the theory really isn't about defining the largest class of functions that deserve to be Sobolev, but yeah, so this is, I hope, enough for one video. So there's a lot. So in my next video, I might give you the actual references with titles and years, so you can also read up on them. So if you missed that video, in case, there is one survey paper by again Piotr from 2003, which I really recommend. The reason being that well, Hajlasz is famous for writing very readable papers in general, and this one being a survey paper is especially well written, very careful. So he was my advisor, and I know how he approaches it. So he basically writes so that even graduate students can read. So if you want kind of a not too technical, well, it does have actually new results in it, and it's but if you want something that goes slow and gives the background and story behind this, so this is called Sobolev spaces on metric measure spaces, and the publication is in Contemporary Mathematics volume 338, again 2003. So you can go to this one because by that year all these spaces that we see here had already been defined, and except for this result of Keith and Zhang, many other things were known back then. A lot has happened since then, but if you only want to get the basics, that paper should be a good starting point. It's about 46 pages long. Okay, so if you have any questions, please do put them in the comments. And thanks for watching and have a great day.